In this example, we're going to solve this quadratic inequality and then graph the solution set on a number line. So the first thing we need to make sure is that all the terms are on one side and we have 0 on the other side. And since this is quadratic, we're going to go ahead and try to factor it, and we're going to set those factors equal to 0 so we can find the critical numbers. So I know that when I try to factor this, the leading coefficient is 1. So I'm just looking for numbers that are factors of negative 21 that add to negative 4. So I know factors of 21 are 3 and 7. And since this is a negative 21, I know one of these is positive and one of these is negative, the larger of which is negative. So this 7 is bigger than the 3, so he's going to be negative, meaning this guy is positive. And I'm going to set that factorization equal to 0 so I can find the critical numbers. So x plus 3 equals 0, x minus 7 equals 0. So I know we have x equals negative 3 or positive 7. So we call these the critical numbers because something interesting is going on there. So I have negative 3 and positive 7. And I know that that's where my circles are going to go, whether they're open circles or closed circles, because those are going to function as my boundaries. And since this is less than and not less than or equal to, I know I have open circles at both of these numbers. Okay, so I'm not sure now, am I going to shade the left or the middle or the right or maybe multiple sections? So I'm going to go ahead and grab some test points. 0 is always a good test point as long as it's between a negative and a positive. And then maybe up here I can try 10, or down here I can try negative 10. We just need a number to be the representative for this entire region, and it only takes one number. So let's go ahead and try my 0, and we're going to plug this test point back into the original inequality. So 0 squared is 0, minus 4 times 0 is 0 still, so minus 21. So a negative 21 is less than 0. Well, yeah, that's true. Negative 21 is less than 0. So I know that I'm going to shade this piece, at least. Okay, so let's go ahead and grab the other points. Negative 10. So negative 10 squared is 100, and then plus 40 is 140, and minus 21. Well, that's much too big. That's not going to be less than 0, so that's going to be a no-go. 10, you're going to see the same thing. 10 squared is 100, minus 40 is 60, and then that's still not going to be less than 0. So here is the graph of our solution set. All the numbers between negative 3 and positive 7, but the boundaries, negative 3 and positive 7, are not included in the solution set because our inequality was not less than or equal to, it was just less than. In this example, we're going to solve this quadratic inequality and then graph its solution set on a number line. So the first thing we need to make sure is that all the terms are on one side and we have a 0 on the other side. So this 15 needs to bounce from the right side to the left side. So we're going to subtract 15 from both sides. So we'll get 2x squared plus x minus 15 is greater than or equal to 0. So we're going to work on factoring this so we can find the critical points. So I know that 2 times negative 15 is negative 30. So we want factors of negative 30 that add to positive 1. So 5 times 6, one of them will be negative, one of them will be positive. The larger is positive. So I'm going to rewrite that linear term as a minus 5x plus 6x minus 15. And we're going to set this expression equal to 0. So when I have it factored, I can set each factor equal to 0 so I can find the critical numbers here. So I'm going to do factor by grouping, pull out an x and get 2x minus 5, and then pull out a 3 and get 2x minus 5. So my factors are 2x minus 5 and x plus 3, each one of which I will now set equal to 0. So I have x equals 5 halves and x equals negative 3. Or I could say 5 halves or negative 3 this way. And these two numbers are going to be my critical numbers that I'm going to use. So whenever I do this, I'm going to now graph my number line. And then I have my -3 and my +5/2. These are my critical points. They're my boundaries. And based on the original inequality that was greater than or equal to, I know these are going to be closed circles. Okay, so now I need to grab some test points to kind of see, well, where am I going to shade? Where are the solution sets going to be? So I have a 0 in here I could choose because it's between a negative and a positive. 5/2 is like 2.5, so I could try 3 as a test point, and then maybe -4 as a test point. Okay, and these points are going to go back into one of these original inequalities. So I could use this one right here since it's greater than or equal to 0. So let's go ahead and plug in 0. So 0 plus 0, and then -15. So we have a -15 is greater than or equal to 0. Well, that'd be a no. No, because a negative number is not greater than or equal to 0. So let's try +3. So 3 squared is 9, times 2 is 18, plus 3 is 21, and then -15 is 6. So 6 is, yeah, that's bigger than 0. So that one will work. So I'll go ahead and shade that one right now. Okay, and let's try -4. So -4 squared is 16, times 2 is 32, -4 is 28, and -15, yeah, is still greater or equal to 0. So this side also will be shaded. So the solution set then for this original quadratic inequality is given by this graph. In this example, we're going to solve this cubic inequality and then graph the solution set on a number line. So the first thing we need to do is to make sure all the terms are on one side of the inequality and we have 0 on the other. So I'm going to go ahead and put all the terms on the left side because that's where my leading coefficient is positive. So it'll be a -4x and a -20 will be less than or equal to 0. So I have 4 terms, so I'm going to go ahead and do factor by grouping. I'm going to pull out an x squared, and I'm going to be left with x plus 5. Then I'm going to factor out a -4 and be left with x plus 5. And when I finish, I'm going to have x squared minus 4, which actually can factor down more. It's a difference of squares. So that'll be an x minus 2, an x plus 2, and an x plus 5. And I'm going to take all of these and set it equal to 0 so I can find the critical numbers here. And the critical numbers will function as boundaries of my solution set on my number line. So x minus 2 equals 0, well, that gives me a positive 2. X plus 2 equals 0, that gives me a negative 2. And x plus 5 equals 0 gives me a negative 5. So on my number line, I have 3 critical points. I have -5, -2, and +2. So I would like to go ahead and do a test point for each region in here. So between -2 and 2 I know is a 0. Between -5 and -2 I could try -3. Over here I could try +3 and maybe a -10 down here, just because 10s are easy to work with. Okay, so we're going to plug each test point into the inequality, and let's go ahead and plug it into the one where I have 0 on one side. This will be a lot easier to maneuver. So let's try the 0 first. So the 0 is going to zero out all these x's. So I have -20 is less than or equal to 0. Well, that's true. Okay, let's try +3. So 3 cubed is 27. And then 5 times 3 squared, so 5 times 9 is 45, so 27 and 45. -12 minus 20, that's definitely a positive number, so that's not going to be less than or equal to 0. So -3 is -27 plus 45, let's see, plus 12 minus 20, and that's going to be positive, so that's not going to work out. And let's see, -10, so we have a -1,000, and then plus 500 is -500. Yeah, that's definitely going to be negative, so that will work as well. So I know I have these two regions which need to be shaded, and the other two will not be shaded. So since it's less than or equal to, I know that my boundaries here will be closed circles. So I'm going to have closed circles at all three of these values. And then I'm shading the left side over here. I'm also going to shade in between -2 and +2 because that region also gave me a true value. So, given the original cubic inequality, we have factored it, we found the critical numbers, and we used test points to plug in to make sure kind of what was true, what was not true. And here is the solution set graphed for our cubic inequality.